z. So if f of z is analytic, we know what analytic functions are. We can do derivatives. They have convergent Taylor series. They're well-behaved functions. If it's analytic, inside and on a closed curve C, a simple closed curve C, This just means, basically, I actually mean that the domain that this curve C is on is simple, meaning that the domain is one connected region. It doesn't have two disconnected regions in the domain of analyticity. But if f of z is analytic inside and on a closed curve C, and if I have a point A is inside C, so this point A is inside my closed curve C, then the following integral formula is true. And the following integral formula is that the integral, the closed integral around this contour C, and again, the convention is to go counterclockwise. The reason is because counterclockwise, again, this is historical, kind of when you write textbooks, you would think of the orientation that makes the most sense. And going counterclockwise, if I integrated a logarithm, or 1 over z minus a, that would be what would cause me to go up the spiral logarithmic staircase to gain positive 2 pi I of phase, whereas if I had this going in the clockwise direction, I'd be going down and spiraling, and we don't want to go in a downward spiral. So this convention is to do a counterclockwise curve C. So the Cauchy integral formula says that if I do a contour integral over an anti-clockwise contour C that contains this point A of f of z over z minus a dz. Remember, f of z is analytic. So if it was not divided by z minus a, then this integral would equal 0. But because I have kind of manually multiplied this by 1 over z minus a, which remember is the only kind of function 1 over z minus a that if I do an integral around its singular point, I actually pick up 2 pi I of phase. That's what we showed in the last lecture. This integral equals 2 pi I times the function f evaluated at that point A. So this doesn't seem implausible, but it also doesn't seem obvious. It doesn't seem at all implausible that this could be true. We know that if f of z was 1, and I had integral of 1 over z minus a, I would have 2 pi I. That's what we showed in the last lecture, essentially because that would give you a logarithm, and if I integrated that logarithm over a closed orbit, I would gain a 2 pi I of phase. So it's not entirely implausible that I would evaluate f at that point A, but it's also not entirely obvious. So this is kind of a very important, important formula, important theorem, and I'm going to show you why this is true. It's actually pretty easy to show. Good. Simple to derive, so let's see how to do this. So this is pretty simple to derive. Don't drink and derive. So you have the integral of f of z over z minus a dz. And what we're going to do is we're going to break this up into two integrals in kind of a cutesy way. So what we're going to do is we're going to say that this equals the integral of f of a over z minus a dz plus the integral of f of z minus f of a over z minus a dz. Now, this seems like, how could this possibly be benefiting me? I'm literally just taking my integral and I'm saying, okay, well, it's f of z minus f of a plus f of a. I've just added, I've subtracted f of a here and I've added f of a here. Seems like, I didn't really do anything. But what we're going to be able to show is that this function adds up to 0, and this, of course, is equal to 2 pi I f of a. So we're going to call this integral integral 1, and we're going to call this integral integral 2. And I'm going to solve each of them separately, and that's what we're going to do. This one's trivial because f of a is a constant. And so I can move that constant outside of the integral, and the integral of 1 over z minus a over a closed loop containing a is 2 pi I. So the integral 1 is obviously equal to f a, integral of 1 over z minus a dz equals f of a 2 pi I, which of course is what we are expecting, so that's good. And so all I have to do is show that this integral I2 equals 0, and I have proven what I need to prove. So now we need to show that I2 equals 0. So to show I2 equals 0, what we're going to do is we are going to deform this contour C. We're going to deform C into this thing I'm going to call C delta, which basically is shrink wrapped around that point A. We're going to kind of hug that point A and take the limit as that radius goes to 0 of this C delta. So we're going to define this curve C delta. And again, because the function f of z and f of z over z minus a, actually, that whole function is analytic everywhere except z equals a. Remember, f is analytic, and 1 over z minus a is analytic everywhere except z equals a. Then I can, by the Cauchy-Goursat theorem, I can deform my contour all the way down until it's super duper close to that point, as long as I don't cross through it. As long as I don't cross through a singularity, the function is analytic everywhere outside of that point A, and so I can deform this thing down as close as I like to that point A. And so what we're going to do is we're going to basically take the limit as delta goes to 0, the kind of radius goes to 0, and prove that this equals 0. So that's what I'm going to do now. And this is going to rely on a kind of idea from calculus that I'm pretty sure almost all of you have heard of. You might not really remember it. This idea that we have kind of delta epsilon proofs. Okay, this if I have a continuous function, and analytic functions are basically continuous on steroids. So if I have a continuous function, then I can use kind of these delta epsilon proofs to bound the behavior and the rate of change of my function in neighborhoods. So since f of z is analytic around this point A, we can choose a delta such that we can choose a delta such that f of z minus f of a is less than epsilon. So this is a standard delta epsilon idea from continuous function theory, from real value calculus that we're used to, is that because f of z is analytic around a, near a, what this means is that f of z, and remember, f of z is actually analytic at a. F of z is analytic at a, around a. F of z is analytic everywhere inside of C. It's only this 1 over z minus a that's not analytic. So f of z is analytic at a. And so what that means is that as I get really, really, really close to that point A, for that radius delta, for any epsilon I like, no matter how small this is, if this is 0.001 or 0.00001, whatever I choose epsilon to be, I can find a delta close enough that f of z minus f of a is within that epsilon. That's a delta epsilon proof. So I can choose a delta, a radius that's close enough to a that this is true for any small epsilon greater than 0. And so essentially what that means is that my integral 2, which is the integral around C delta of f of z minus f of a over z minus a dz equals, this implies that the norm of I2 is going to be less than or equal to the norm of this thing, which is less than epsilon, so this whole norm is going to be less than or equal to the integral of epsilon over z minus a dz. This is kind of like that ML bound I was showing you. And this is going to equal 2 pi I epsilon. But this was true for any epsilon. I could find a delta that makes this within epsilon. So I can take the limit as epsilon goes to 0, and I just can find that I basically, there is a delta that will, if I constrict delta to 0, this epsilon will go to 0. So this is true for all epsilon greater than 0, so it has to equal 0. So this has to equal 0.